doing is merging that result with bit 0. So what's happening there? We are to calculate G2 to 0, right? So if we rewrite this, what we can actually tell is G2 to 1 plus P2 to 1 G0. Do you remember this? This is bit 210. Instead of just calculating carry like this, we are calculating generation condition here, and then generation condition here, times propagation condition here. So that's this term and generation for 2 to 1. So we are merging these carry generation propagation condition for 3-bit range by calculating 2-bit range first and merging 1 bit later. Then we can calculate this 2 to 0. Okay? Then what about 3 to 0? Okay, that would take too long time. Okay, let's go higher bit. 8 to 0. What is it doing? It's taking this gray cell. Its input is from this black cell and this bit 0. So bit 0, this is taking P0, G0, so no problem. Then what is this black cell generating? So this is for bit 0, so this should generate GP value for bit range 8 to 1, right? Because that way we can generate 8 to 0. The range 8 to 1 is covered by this, range 0 is covered by this. So if you merge those two, that will be 8 to 0, right? Then how is 8 to 1 covered? It's again divided by these two paths here. So here, this black cell calculates 8 to 5, and this black cell calculates 4 to 1. So if you merge that, 8, 5, 4, 1, so that's 8 to 1, right? Then these can be also divided like this. So this 8, 5 is calculated from 8, 7, 6, 5. And this 4, 2, 1 is calculated by 4, 3, 2, 1. So basically, you have a tree of carry calculation. Although you, at the end, you are looking at very wide range, but at each stage, you have a binary tree, right? You divide. You have this 2 branch here. You have 2 branch here, and each of them have 2 branch here. And eventually, the final 2 branch covers entire area. This is covered, right? So basically, this is merging carry for different bit ranges systematically. And then later you merge for a certain range. And because each bit position requires different range, so you have to actually generate structure for each bit position. So for example, here you need this one and somewhere here. So 11, 4, 3 to 0. But for covering 12 to 0, rather than having just 12 and bit, 12 bit and then merging this one and this one, you would prefer to have binary tree that can systematically merge. If you just add 1 bit like this, then this is again will be ripple carry either, because on 13th speed, if you want to take this again, then that's 2 stage, so that's ripple carry either. So you want to systematically merge 1 bit, 2 bit, 4 bit, 8 bit, something like this. So that's why this structure has this tree structure here, here, and then goes here, 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 something like this. And eventually, so for the highest bit, eventually it actually covers every single bit, because we have to, right? We have to consider all the generation and propagation condition for each bit position for calculating the highest bit carry. So that means this carry calculation will be the bottleneck, which should be true, right? If you have a wider adder, then always the highest bit carry takes the longest time to calculate. So that's also true here. So one thing you should note is this is gray cell, this is black cell. Okay, why is it different? So difference is gray cell and black cell means for black cell you calculate P and G, but for gray cell you only calculate G. So if you need to calculate propagation condition for certain bit range, you need to use black cell. But if you don't have to calculate propagation condition, you can use gray cell. So how can it be determined? If your calculation result is used by other gray cell or black cell, you should be black cell, because you're gonna take the propagation condition from this result and then you're gonna use it in the later stage. So in that case, you need propagation calculation. That's why you have black cell inside here, whereas if you're not gonna take this output for another stage of carry calculation, you use gray cells, because you don't need to calculate propagation condition for that portion. And this buffer is just kind of representing that if you have a long wire, you might want to buffer it up. So it kind of matches the delay. All right, so you can see that number of stage here is log the order of log 2, because every time you split you have 2 branches, and then eventually your branch should cover individual bits. So if you have 1 stage, you can cover 2 bit. If you have 2 stage, you can cover 4 bit. 3 stage, 4 stage, right? So that's easy to track. And you can see that carry calculation is very redundant in this structure, right? Like, let's say 13th bit carry is taken here, here, and then here. This is taken here. Basically, these 2 paths, and even in this 3 path. Basically, this 13th bit carry condition is used for calculation in these 3 paths. And even for this case, bit 5, then you are basically using this result for like all different paths here. So it's very redundant. But we need those redundant calculations because for specific bit position, we need different range, right? So that's why it's redundant, but we have many copies. Okay, so this is the Kogge-Stone adder, and there's actually some variants of these adders. Okay, so you can see that there are so many black and gray cells. This is like very regular structure, but very dense structure and very redundant calculation. So to reduce number of those operation, there are a few variants. First is Brencom, which is shown here. It basically have merging tree on the forward tree on the one side. So basically, in this upper part, it merges certain range. So here merge, 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 merge. But you can see that for this bit position, you actually just need this merged result and this bit, right? So instead of having this kind of tree here, what this adder So in Kogistone adder, regardless of bit position, you would have something like this structure, and then you split that, and then you split that, something like this. But in this adder, what they do is you merge only in this direction, and then if you have remaining like 1 or 2 bits, then you just merge those 1 bit here, something like this. For 4 to 0, you take this result and then merge 1 bit here. So Kogistone, you don't do that, but here you are, you have this backward tree where you merge 1 or 2 or 3 bits, remaining bits on this side. So this reduces number of redundant operation, as you can clearly see here. If you track all these, you will still cover all the range. Like if this bit 14, you cover 14, and then 13, 12, something like this. So it still covers, but you have fewer number of gray and black cells. And of course, the cost is longer delay path, right? You can see that the worst case delay path is here, and you can see that you first merge carry for the lower bit here, but for the upper side you merge carry for this bit position, this bit position, this position, something like that. So it actually has twice more stages, so it's twice slower compared to Kogistone adder, but the power is 2 log n minus 1. 1, 2, 3, 4, 5, 6, 7. I think minus 1. So this is an approximate order. So much less power consumption, and of course smaller area, but longer delay. So if your penalty is like 50% performance penalty, that's huge, right? But your power consumption is also, I think, almost half, something like that. Yeah. So that's good trade-off to have, right? And there's another type of